Hello. Can everyone hear me?
Yep, we can hear you.
Great. And you should be able to see my screen.
Yep, that as well.
Okay. So I think we started 1:15, right? So we should start now. So my name's Alistair, and I work for Western Digital as part of the research team. And probably a year ago, we did a lot of the software bring up for the RISC-V hypervisor. So I'm not going to go over what RISC-V is. I think everyone knows that, or if anyone doesn't, I can go over that. Just type in a little chat thing. But otherwise, I'll just jump straight into what the hypervisor extensions are, and then Bobby's here, who has sent some RFC patches to the Zen mailing list for the hypervisor extensions. And we can discuss after that.
Right, and I think I'll probably also have a couple questions for you as well. So I think, yeah, this will be great.
Okay. So the RISC-V hypervisor extensions, the way the RISC-V architecture works is it's very basic. It's basically just add and branch instructions, and then you have extensions that add everything on top. So the RISC-V hypervisor extension adds support for running hypervisors. The latest version is the 0.6.1 draft. So a draft spec means that it's not ratified, it's not frozen, it's still subject to change. In saying that, it's a pretty long, and it's pretty late in the draft process. So we're at the 0.6.1. We started originally with 0.3, so we've had multiple revisions with multiple input from lots of software projects like KVM and QEMU, and lots of hardware designers. So we're thinking and hoping that the 0.6.1 is almost frozen. We're almost there. We're mostly just waiting on a hardware implementation now. Generally, the specs won't get frozen until there's a hardware implementation to kind of show viability. So the RISC-V hypervisor extension is much more similar to the ARM VHE than it is to the original ARM virtualization. So it's much more accommodating to your operating system hypervisors like KVM, but for Zen it works as well. It doesn't compromise and affect the working with Zen. So Western Digital did the QEMU, the XVisor, and the KVM ports, and we've been maintaining and updating those. The QEMU port is upstream. The current upstream version is a little out of date. It's the 0.5 version where the patches are waiting for review for the next one. And KVM patches on list. KVM, the Linux kernel won't accept a draft extension. That's their policy, while QEMU doesn't have that requirement. So the KVM is waiting for the extension to be frozen. And XVisor, which is a small bare metal hypervisor, has upstream support for the latest version. So the way the RISC-V hypervisor extension works is it changes your normal M, S, and U for machine, supervisor, and user space modes, which would be similar to the ARM EL3, EL1, and EL0. So firmware, operating system, and user space, and it changed it to look like this. So your machine mode, I don't know if you can see my mouse, but the machine mode down the bottom stays the same. You can't virtualize, or you don't virtualize the firmware. The firmware stays the same. On top of that, you run your HS, your hypervisor supervisor mode. And so for Zen, that's where Zen would run. For KVM, that's where Linux and KVM would run. And if you weren't using a hypervisor, that's where your OS would run. So Linux or whatever else you're running. And then your virtualized world over here on the left would be then VS, which is your virtualized supervisor, so your virtual operating system, and then your VU, your virtual user space. And it also allows you to have a non-virtualized user space, just U mode. And there's extra CSRs and extra functionality to handle this. So the cool thing about the RISC-V extensions are that operating system doesn't need any awareness. If you don't want to use the hypervisor, you can just run with the hypervisor extensions and no changes. You'll just run a HS instead of U mode, insert HS instead of S mode, which will just mean you have some extra registers you could access, but you don't have to. For Zen, this works really well as well, because we can boot Zen in HS mode, and then Zen can control everything from there. And Zen can have user space components in U mode if it wants. I'll just check. If anyone has questions, just shout out. I think the right S and no HS. Oh, yeah, probably. So the CSRs. So RISC-V has control status registers. Is that what it stands for? Now I don't remember. But yeah, CSRs that basically control everything you're doing. And so in HS, which is called V = 0 in the RISC-V specs, the virtualization's off, you get all your normal SCSRs, which are all the things that a normal operating system needs. So SATP to set up the page table, things like that. You have all those. Then you have HS CSRs, which are new with the hypervisor spec. And that gives you access to things that a hypervisor needs to control, like guest delegation, guest interrupts, two-stage page table, things like that. And then you have VS CSRs, which are shadow copies of the guest CSRs. And so when you swap from V = 0 to V = 1, which means your virtualization is on and you're running in your virtualized guest, the hardware will switch VS and the S around, which is the pointer, but it switches them around basically. So the VS is then accessing what your guest is then accessing what used to be the VS CSRs. So this allows your hypervisor to read and write the CSRs. It can save them and restore them, and do whatever else it needs to do. And the next slide, I think. Well, so yeah, and you can also then use this to set interrupts. There's a VSI. Oh no, it's HSIP. Yeah, so it doesn't matter. So the RISC-V hypervisor extension also includes a two-stage MMU. So the MMU is very, very simple for the two-stage part at least. It basically just loops through the same MMU twice. There's a few changes in the way the length of the page table entries, but it's basically the same. So you can just set it up the same way, and the hardware kind of just reiterates to itself. So the first stage is the guest virtual address to the guest physical address, and that's what the guest will control. And the second stage is the guest physical address to the host physical address, and that's what's controlled by the hypervisor. RISC-V, the ISA spec has no IO MMU. That's being discussed, but that's not there. And there's also no virtualized interrupts. The two things to keep in mind. So the interrupts can be injected from the hypervisor using the HVIP, which basically will then write it into the VSIP, which is the interrupt pending CSRs. It's a little complex to explain, but it kind of, when you read the spec, it makes sense. Yeah, and that's the end of my slides. So all the standard things, you can inject timer and software interrupts from a hypervisor. And you can do trap and emulate MMIO accesses, which is what Xvisor does to emulate devices. So that's a quick rundown on the RISC-V hypervisor extension. Like I said, there's QEMU support, KVM patches, Xvisor support, and so now we're just missing Zen support. And Bobby sent an RFC to the Zen mailing list a little while ago. And do you want to talk about what you're doing, Bobby?
Can I ask you a question, Alistair?
Oh, yeah.
So for interrupts, so you're saying that there is a way to inject interrupts in general, like a trigger delivery, but not quite an interrupt controller with virtualization support. Is that what you're saying?
Yes. Yeah. So every interrupt will go to the hypervisor, and then the hypervisor decides to inject it into the guest. So the hypervisor basically writes it into the HVIP CSR, which will set it in the guest, and then when it swaps back to the guest will have a pending interrupt.
Okay, and pending interrupt of the number of the RQ number chosen by the hypervisor as written on the CSR register?
So the CSR will let you write. The way the RISC-V CSRs work is you can set the type. So you can set an external interrupt, a timer interrupt, or a software interrupt. So the guest would, the hypervisor would say there's an external interrupt, and then the guest would do whatever it normally does to handle that. And the hypervisor would be emulating a click, which is the interrupt controller. And so the guest would then read the click, which would trap and emulate to the hypervisor, and the hypervisor will return the number of whatever UART interrupt or whatever it is.
Thank you.
So the interrupts are slow, right? All this trapping is slow. So there is definitely need for virtualized interrupts, and that's being discussed, but that's kind of separate to the ISA. That would be more in the interrupt controller.
Makes sense.
So I have one very quick observation. You said about the second stage tables walking the same as the first stage. That's exactly how AMD do second level page tables on x86. Intel chose a different way of doing it. We certainly have code that looks like that in Zen already at the moment.
I think that's good. It's not exactly the same. It's very similar. There are, if you look at the code, you can get an idea. There are a few differences, but it's very similar.
So it will be similar to ARM, where stage 2 and stage 1 are roughly the same, but with a different values in the each entry.
Yes.
Okay.
And like traps are handled differently, right? If stage 1 or stage 2 fails, you trap to different places. Actually, the exception raised is different.
Okay.
So regarding the PLIC, primarily, I guess my question is what we're hoping for is that we can eliminate the trap on the claim and completion interaction that a guest will have to be performing with the PLIC. Is there anything that I'm missing there in terms of what PLIC supporting virtualization really means, besides taking that the ACK and and kind of in the ARM world, the ACK and the EOI, and taking that out of having to be trapped into the hypervisor and moved into hardware?
Yeah. So I mean, the PLIC is not part of the hypervisor spec, right? It's not part of the ISA. So there is a different PLIC spec that is, I think, about to finalize the initial, standardize the initial PLIC. So after that, hopefully one of the next things to do would be add virtualized support. I'm not sure how. I think John, who wrote hypervisor spec, has plans there, but I'm not sure what they are of how to not to have to waste having the hypervisor claim and complete all the interrupts. Yeah, I don't really know. I know it's definitely, everyone agrees it's a problem. This is not what we want in the end, right? But for now, it's what we have.
Cool.
And it doesn't waste effort now, right? Supporting the hypervisor spec without virtualized interrupts is not wasted effort. When virtualized interrupts come, you can just update it and support that. So it's not, you're still building along by adding support. And so that's why it'd be awesome to get Zen support in.
So, I mean, have you compared what the ARM VGIC and Intel the APIC implementations to see kind of what works, what doesn't work, and what seems to be needed?
I have not. I haven't looked at the virtualizing interrupts really at all. I think everyone's kind of on the page of let's get the hypervisor spec frozen and then look at things like virtual interrupts, IO, MMU, things like that.
Right. So, I mean, one thing to try and think ahead is to think about what your final interface to the guest you want to look like. So it would be ideal if after you wrote a guest that was going to run on Zen, without the virtualized interrupt, without the hardware support for the virtual interrupts, that then once the hardware support came through, then everything would just magically work and you wouldn't have to make any changes to the guest.
Yeah, so I think that's what, for example, in XVisor we do now. We show a guest of some devices and say they're there in the device tree, and we trap and emulate all the accesses, and we pretend that the interrupts are coming from hardware and those virtual devices, but they actually trap into the hypervisor, and the hypervisor then claims them and sets them and all this stuff. So with a virtualized interrupt controller, that should just stop trapping, right?
Right.
I'm more on the QEMU side than the design.
And just a comment on the like comparison with x86 and ARM. The PLIC, to my mind, seems very GIC-like. I'm not super familiar with Intel, so it might also be similar there. But at least the interaction of, you pull the interrupt number and then acknowledge back with that interrupt number. It's memory mapped. It seems very GIC-like. So the structures that are there for ARM would probably fit well.
Okay. Revert IO. I don't think we actually have Vert IO then yet. I know people are working on it for probably the same reasons, but before you can actually get a guest working on, I mean, I think at the moment you'd have to either implement some, because there are sort of there's a disconnect between how Zen works and how KVM works that make Vert IO. There's a bit of an impedance response there. Stefano or someone else might be able to talk more about that, but
I don't think probably Alistair meant that Vert IO need to be the only one supported. I bet. I think, I mean, PV drivers, when we enabled them for ARM, there were very, very few things that needed changing to enable them, and probably they would work fine on RISC-V. That doesn't mean that Vert IO shouldn't also be there at some point, right?
I was just responding to a chat here where you said Vert IO first, but
I think Vert IO is going to.
I was just confused, I think. I thought they were both there, and Vert IO makes more sense to me because that's what I'm used to.
Vert IO is going to require much more work on Zen, at least, because you will have to trap on forward everything to the user space, which means IOREC. I've tried to do it on ARM as a POC, and there is quite a bit of work to do something properly. Whereas in case of Zen PV drivers, you will barely have a few things to set up to make it work anywhere, at least on the Zen setup.
Okay, then definitely do. That was wrong. Do PV first. In XVisor we do Vert IO, but it's a different hypervisor. So.
There is definitely work happening on Vert IO for Zen. I know a couple of companies, not sure if they're on the call, looking at Vert IO on Zen, and they have a POC for ARM. Hopefully it should be public in a few weeks' time. From there, I do hope that a lot of code can be reused on RISC-V, given that it's not very specific to ARM, the code.
Like the next main thing would be, how do we get RISC support in Zen?
So what's the state of the patch series? Have you gotten the kind of review you need, or if not, then there's basically ways that we can kind of escalate it. So at the moment, each developer kind of keeps their own list of things and their own timeout. But sometimes what happens is things fall through the cracks. People don't notice that it hasn't been paid attention to. So if you send an email, if you send a patch series and you don't get any feedback within 2 weeks, then there's things you can do to escalate it to make sure that it stays live and that it doesn't get dropped. And we may need to basically kind of specifically recruit some people to shepherd it, if that makes sense.
Yeah, definitely. I feel like I've gotten good feedback so far. It was just an RFC patch set, so very preliminary. In terms of like functionally, what the patch set supports is it gets the hypervisor to the point that it's mapped itself, set up virtual memory, VMAP, IO remap, and the mapping infrastructure that hooks into the common code to make mapping in the hypervisor's memory space possible, and to the point that you get some serial output, and that's where it stops. So it really mostly just sets up virtual memory, and there's a lot of I would say a lot of extra code that doesn't need to be there. So I was basically going to wait a little bit to take the feedback I've gotten, incorporate that, and then get something a little bit more functional to the point that maybe actually have some more of the code around getting guests up and running before I push more for a more I guess thorough look at it, because I think right now to have people dig through more closely might not be the most effective use of time, just because there is not a lot there, and I think the bigger questions will come about later. Okay. But I do have one question that relates to what I have so far, and that's related to the talk on direct mapping. So the patch set right now just uses direct mapping by default because it was just the easiest route to go. But now that I'm seeing all this work done to avoid that, is that something that, is there any reason to support direct mapping at all, except for convenience to writing the code, because it's just easier to implement? But from actual like an end product viewpoint, is there any reason to support hypervisor direct mapping, or should that just be avoided from the beginning?
So it's complicated. That's the answer. So first of all, I'm kind of surprised. I mean, it shouldn't be a lot of work to enable like a normal memory allocation. But that said, it really depends on the fact that you don't have an IOMMU. I think that's one of the key points. So the reason is, well, RISC-V, I think it's very embedded at the moment, like a bit like ARM, and so device assignment is usually a key part of a setup, and you cannot do device assignment if you don't have an IOMMU at all without direct mapping. So I would argue that on RISC-V, until an IOMMU is around, direct mapping is actually quite important. Otherwise, you're not going to be able to assign any device.
There's something different between direct mapping and identity mapping, and I'm not sure
maybe I misunderstood.
Bobby was referring to what do you think he's referring, or something else.
Yeah, but Bobby's talking about basically
the direct mapping Zen, yeah.
Direct map in Zen. So that when you do on 64-bit Zen, right? When you do map domain page, it just says, oh, right, here it is, and it gives you a virtual address. It doesn't actually do any real mapping most of the time.
Okay, sorry, I'll shut up then.
No, I mean, that's something that I was going to ask anyway, Stefano, because I think it's also quite relevant, the fact that they don't have an IOM-MIU, so that they will need to resort to an identity mapping for DOM0, at least, like you do on ARM, which is something that I think has caused some pain on ARM, if I recall.
So the problem is, so you have to write the code in a slightly different way, right? When there is identity mapping. So typically, what we like to do in Zen is, this is the environment for the guest, this is the address for the interrupt controller, all fake. This is the start of memory, all fake, and this is a guest memory map. And that's one of the first things we started doing, right? But if you're going to do the identity mapping, it makes sense to make the identity mapping of everything. So map the interrupt controller at the same location, and the memory start the same location as the physical memory start, which actually I think, in retrospect, for a very embedded configuration is probably preferable. But yeah, so it's not difficult to support both, except for the fact that I haven't found a way yet, easy way at least, to fool the memory allocator in Zen to leave alone the pre-allocated memory area.
I don't think this is difficult because we've been doing it for live updates at AWS. However, the problem with the one-to-one mapping is you don't want to bake that in Linux as we did on ARM, because no, we can't remove it for DOM0. It's impossible to remove it without breaking DOM0. So if you were going to add a one-to-one mapping for DOM0, then I would strongly recommend to have a knob somewhere to allow to remove it easily at runtime.
Yeah, that's a great suggestion. Like even just a flag that you set and you check at the beginning, and even if it just errors out, if the flag is not present or something, it at least will give you a way then to take it out.
Okay.
So for the direct map, meaning the mapping of the whole memory, I think there is no problem not having it. So on ARM32, we don't have it, for instance. So I think that's no problem at all.
Okay.
It really depends what you expect in terms of emulation. If you have emulations that require to do accessing the RAM every time, and you need to do map on map, it's probably going to have a cost. I don't know how you plan to do your virtual controller or things like that, but I know that the ITS is relying on the direct mapping, and if we're going to remove the direct mapping, then it's going to be much lower. So yeah, it's a mix of security and performance.
But I don't think I don't imagine RISC-V as anything as complicated as the ITS yet, at least. I would imagine. But who knows what's going to come up?
Sure.
I mean, from my understanding,
Okay,
even
cool.
on x86, the plan is to keep the two, at least in short term.
No, that answers my question too, because so that's great. So it's not something that we would necessarily regret having spent time implementing. Cool.
And I think it's this kind of architectural question that it's really good to get early feedback on. I mean, so like the question is, should we have a direct map? Should we have a one-to-one mapping for DOM0? Things that have obviously caused problems in other for other architectures.
One thing that I know ARM had some difficulty with, and I don't know whether that was just because of the way the initial implementation was done, is there were certain difficulties with cache flushing that ultimately caused, I think, some significant architectural problems. I don't know how much that will translate to RISC-V, and I don't know much about it. Maybe one of the ARM folks can comment.
What specific problem you're mentioning about cache flush?
There was some difficulty with the set way, flush by set or way.
Oh, yes.
Julie and you particularly know about that.
Yes. As ARM did virtualization afterwards, there's quite a few things that were not easily virtualizable. But the way forward now is to try to remove everything from the the way forward is to get the guest to remove any use of these instructions. We still emulate it, but it's going to be very slow. There is speaking about cache, there is a couple of problems to think about. Is in the case of ARM, we decided that all the hypercall buffer are going to be in cacheable memory. However, if you're looking at platform where there is no MMU, small embedded device, then you're not going to be able to use the hypercall interface. I'm not entirely sure if it can be easily solvable, other than having the guest to do the cache maintenance, but that's something to bear in mind when you're trying to design the hypercall ABI, or at least the architecture part of the hypercall ABI.
Could you just encode the flash inside of the hypercall page or something like that?
We don't have any hypercall page.
Oh, okay.
Even that is because you need to flush everything, the buffer, the hypercall. If you have buffer inside a buffer, then you have to do also, etc. So I don't think the hypercall page will be big enough to do it.
Yeah. If you have pointers inside of the hypercall structure, then you need to flush those.
Yes.
Yeah. Doesn't the same kind of apply when you do emulation also, Julian, or that's something that's handled differently from hypercalls, I mean? All these caching issues that you mentioned.
Caching is a mess. At least on x86 is really simple. On ARM, it's pretty much a mess, because even if you disable the cache, you don't really disable the cache, which brings to a lot of problems. Yes, emulation is also a problem. If you try to access a memory and you need to emulate it, but it's non-cacheable on the guest, then you're probably going to get some trouble there. Thankfully, there's not much emulations codes where you need to access the guest on the cacheability attribute have not been defined. So for instance, in the case of ITS, even if we need to access the RAM, it's configured the two sides, so the hardware side on the guest defines which cacheability attribute are used. I think the good thing there is, as RISC-V is coming after ARM, we did quite a bit of resolving the caching issue in common codes and in PV drivers, so it should be much easier for them to enable even like memory reordering of instruction, etc. It should be easier.
So I'm sorry, I only joined midway through this conversation. Are we saying that RISC-V, like ARM, is non-coherent between different virtual addresses of the same physical address?
It's coherent on ARM.
then why do you get caching problems on emulation?
If your guest is running with cache on MMU disable, which people have been doing it with U-boot, for instance.
But so x86 is admittedly a bit more complicated in this area, but the mechanics of how memory works is indistinguishable from explicitly mapping it as uncached and disabling caches in the core. So you never get a problem where you've got a mapping that's uncached in one side and no caching in the CPU on the other, and conflicting problems.
You have on ARM, it's a software to deal with it. It's clearly written in the ARM, unfortunately.
Okay, so where does RISC-V sit in this? Does that have a different behavior, or is it the same behavior as ARM?
Hey, Alistair, this is something that cache behavior is not explicitly specified, as far as I can tell, in the specifications. So this would be something that's specific to the actual hardware implementation, if I'm not mistaken. But Alistair could correct me on that.
I think so. I mean, I do most of my stuff in QEMU, so I don't really worry about caches. But yeah, I think that's only a specific. I can double check.
Yeah, and I could look at maybe how one of the Sci-5 chips is handling caching. Since my RISC-V exposure has been based on the QEMU implementation too, I'm not 100% familiar.
Right. Well, the thing is, it's a very important question that makes a large difference on how you go about solving the problem.
This only happens when the MMU's off, the guest MMU's off. Is that what you said? Or did I mishear that?
So on x86 there is no problem because there is no conceptual difference between the guest MMU being off, or straight cache disable mode. But from what Julian has said, there is a difference on ARM between disabling the MMU and having an uncached mapping.
Technically, because of that, the direct mapping is completely wrong on ARM64 also, because you now end up to have two mappings, with one which is uncacheable on the other one which is cacheable. On per the ARM, it's broken. It's undefined.
Right. So I think part of Ian's original question that was, is there anything like this in RISC-V that we can avoid?
Yeah, I think the cache that sounds very implementation specific. But in RISC-V, the MMU must always be on for virtualization. It can't be off. It can be not set, but it's still on.
But then what do you do if you're running a bootloader inside the VM, a bootloader that is expected to run with MMU off? So
you just zero out the SATP register, and it's just like direct mapped, but it's still technically that's what the spec says.
So hardware will behave as if the MMU is on and set in fully ident mode.
Hopefully, yes. I think
I'm a bit concerned by these comments that cache behavior is kind of implementation specific. If you're writing a kernel or a hypervisor, you need to know which cache flush operations to perform and what the architectural interface to that is. Maybe
that's in the ISA. That's in the ISA, but what type of cache you have, it depends on your implementation.
Right. So the ARM problem that we were discussing was that the ARM inherited from pre-virtualization time an architectural flush operation that was very difficult to virtualize. So I don't think that talking about this, and also questions, for example, of coherence I think they're architectural rather than implementation questions, because the software obviously needs to be written with a particular set of assumptions in mind. So I'm confused by these comments that certain things are implementation. I think all the problems we've been discussing are architectural.
Okay, so the hypervisor extension defines new instructions to flush for the hypervisor to flush things. Yeah, I don't know. I think I would have to look at that. I do most of my stuff in QEMU where the first sign of anything, we just flush everything.
Yeah, and I'll double check that the cache portion of the specification, there very well could be more there that I'm not recalling.
Okay, thank you.
We have, what, 3 minutes left? Is that right?
We've got 3 minutes left. There is a break afterwards, so we can overrun a little bit if people are still talking.
Is there anything else anyone wants to talk about, ask in the last 3 minutes?
So I do have some. So I'm interested a little bit more in the mechanics of how to try and start getting support up into Zen, because I think it is an excellent idea to have something that isn't just x86 and just ARM in there. Certainly, in the past, Zen had pretty good split between common code and Arch specific code, and then for a while we got down to x86 being the only architecture, and then we got ARM back in. But even at the moment, there are some areas where we have a very bad split between what is common code and what is Arch specific code. In particular, from the original RFC series to get things to even get things compiling, there are a number of things that identify areas of common code that are actually Arch specific and areas of common code that ought to be compile time configurable. I would like to take the opportunity of identifying these areas to try and fix them. I'm very happy to volunteer to try and fix some of the problems in the current Zen code base that make it hard to port to a new architecture. In particular, that is things like the x86 debug macros that every other architecture currently has to have a zero implementation of, or untangling things like the current atomics, where we've now gained basically three almost identical copies of the Linux generic atomics infrastructure. So issues like that, I would love to be able to take this opportunity to fix, to help make new architectures easier to sort in the future, if that makes sense.
The other thing that goes in that direction is, you cannot really expect to have the full architecture built in the first patch series. If you get a patch series that gets Zen to boot and maybe a bit of DOM0 to boot, that would be an excellent first step, even if you can't really start any DOMU. And then you can build on top of that with the follow-up.
Frankly, I was suggesting something even smaller. Get it to compile first with an infinite loop, or put out a hello world to serial, because that's a hard enough job in its own.
You're right. And then actually, if you're going back in time, that's actually how we did the ARM port initially. I think at the beginning, the ARM port was a hello world, actually. That was the ARM port. Funny enough, but yes. So yeah, I completely agree.
Right, but the ARM port was still several hundred patches to even get it to compile, I recall.
Yeah, and the other point about getting code in the tree is that the sooner there's code in the tree, the sooner the other people can actually start work on stuff, right? So obviously, if the code is churning, if the code can't even boot and it's churning a huge amount, then no one else is going to want to work on it. But once you get to a point where some of the code is stable and then you can start working on one aspect of it. Other people can come in and start working on the other aspects of it, and parallelize things. So that's a big.
Well, but and the moment we have something that even just builds the hypervisor, we can get the build in CI. We don't need to try booting the result, but there are enough times when we break common code accidentally, because there's an implicit assumption. So even having something that literally builds and doesn't boot will still be a good start for future CI.
It'll make it much less painful for you to, to have a 100 patch, series out of tree is super, super painful because stuff is always breaking. And you spend every 2 weeks you rebase, and you spend the first 3 days fixing all the things that broke. So, yeah.
And Andrew, I did incorporate your feedback on that. I went back to the patch set and essentially went to the initial commits and reduced everything down to only what is necessary to compile, and essentially emptied out anything that was unnecessary. So there is an initial set of commits now that all it does is make it so that the new architecture will build, and as you suggested, jumps into an infinite loop. So that is something that I could get up, and we could get into CI. The issue I ran into with CI though is that the CI automation script seems to be built under the assumption that, and I could be wrong about this, but that the build is happening on the architecture that you're building for. So I put on pause all the changes that I was going to need to make that happen, because there was going to be a requirement to either change the script significantly or add in building within QEMU or something along those lines. So I put that on pause, but I could pick that back up in order to make that. I think it would certainly
be used to have some input there. The current automation we've got was the bare minimum to try and get some automation together, and we're certainly happy to try and change that in the future. I don't know how good Docker is with cross-architecture stuff, but a different alternative would be to install an x86 cross-compiler in. That would at least get us some compiling.
We do have some basic. The CI loop just had some basic tests that will spin up QEMU, I think, to run Zen inside of it.
It runs Zen and an XTF test inside QEMU.
Right. So it shouldn't be. I mean, it should be possible for this kind of architecture. I mean, it would just take someone to sit down and make it possible to install the proper version of QEMU and to sort out the build tools so that you can cross compile it. But I don't think it should be a huge amount of work.
I can help with that, Bobby.
Yeah, that'd be cool. It wasn't going to be a huge amount of work. It's just that with the hours I have per week, I was like, maybe I should focus. If upstream is ready to have the minimum build in CI, then absolutely that sounds great.
And we can happily change how the current CI works. No one's suggesting it's perfect in its current form. We definitely do have one attempt to cross-compile some ARM, but we also have a proper ARM system run out of packet.net. So I don't know how much of that is straight up.
Okay. And I do actually have a branch of the that has essentially patches the Docker files to add the RISC-V cross compiler, and so all of and adds a QEMU build that will run the RISC-V build. So to take that all to a upstreamable point shouldn't be a ton of work or time.
So to a point that Julian has just made in the chat, cross-compiling Zen itself is easy because it's a tiny embedded target, and even just getting that is valuable to start with. When you want to expand to the user space tools in DOM0, it becomes a whole different problem. But for initial support, just focus on the hypervisor alone.
Yeah, I've found that to be true because the way I've been building it is simply jumping into the hypervisor directory and building it from there instead of using autoconf from root.
If this were several years into a theoretical future where we've fixed all our ABI problems, a separate thing we were talking about was trying to split the hypervisor and tools into separate repositories, but we've got to fix a load of ABI problems before that is even a possibility to consider. And I think it would make some problems like this easier. But of course, that is a discussion the community has to have at a point where it is a feasible option, and it's definitely not right now.
Right, and now that I think about it, actually, I believe Alistair has some commits early on in the patch set that I think just simply disables building the tools for RISC-V when RISC-V is selected. So, and it's clearly called out in the commit history as something that we don't want to actually do, but is necessary at the moment.
And like I said, it's entirely fine to start with just a build of the hypervisor with an infinite loop and increment from there to get to something that's working.
Cool.
Great. Sounds like we have a step forward.
To be perfectly honest, I do have an ulterior motive here. I know that another group of people are interested in starting Power 9 as well. And in reality, Power 9 is going to have exactly the same problems that you're currently facing here with what to do to get the hypervisor to compile and what to do to get the tools to compile. So these are general problems with how Zen is currently structured, and we really do want to try and make it easier. The thing is, it's not obvious until you're actually doing it.
I would like to point out we are about 10 minutes over time, and the next session will be starting in 20 minutes. So I'm probably going to go take a break, so I'm fresh for that. So obviously, you guys can keep talking as long as you want, but if you need a break, then make sure and take one.
Okay, thanks, George. I do have one question. I'm running into situations where there's a clear common code between ARM and RISC-V, but less so with Intel. I think one of the examples, well, one clear one is device tree parsing. So obviously, right now I've just duplicated the code, and I think perhaps in the Linux world, this I'm not exactly sure how it's done there. Whether that I imagine it's you're not going to find device tree parsing in I don't know whether it's just going to be like a no-op hook for architectures that don't use it, or I can't imagine that being the case.
So the way I would suggest we do this under Zen certainly is to actually move it into common code, but have a kconfig device tree or something like that, which is selected by ARM and selected by RISC-V and a header file, if needs be, a header file with no op stubs for the not selected case. That's how we've gone about trying to separate modules at boundaries. And even within x86, we try and do the same thing for Intel support and AMD support because they can be quite different. So we are certainly receptive to things like that, at which point it would naturally live in common code, even if it wasn't compiled on all architectures by default.
Okay, cool.
I do agree with this approach, by the way. If there is code that can be reused from ARM, then they should be in common codes. We didn't have this need so far because there was only x86 on ARM. So it's going to be different with RISC-V or even Power 9, as Andrew has suggested.
Right, and the other thing is that we had x86 and ARM before we really applied kconfig in seriousness to the hypervisor. So had we had kconfig around better, I don't think we'd have quite done, it wouldn't have evolved the way it did.
I would be happy to help refactoring the ARM codes or even answering questions there to see what we can move in common codes.
Yeah, in particular, I think we will find that there is already quite a mess of header files, and this will probably show up when you attempt to compile a new bit of common code. You'll suddenly find that you include event channel.c, and suddenly a whole load of header files don't work. So I would also be interested in anything like this where we effectively have a header tangle that should be cleaned up before we put new code in. I'm also happy to try and clean up the areas that identifies.
I've tried to do it in the past and it's a bit of a mess, and then
yeah, it's much easier to do it one header file at a time than to try and fix the entire mess in one go. I'm trying to do the same on x86, but a lot of these will probably involve restructuring how the common headers include each other.
Well, I do have some patches that relate to this, where there are some places too where kconfig, there's a couple kconfig options that are not exactly options because if they're disabled, I think PDX might be one of them actually, where I'm not sure if Zen will compile without PDX actually.
It won't. I've got a project that I've been attempting to make that work properly and then delete it because PDX was added to x86 for a Fujitsu system that never ended up shipping, that had one RAM bank down at 0 and one RAM bank up at the top of memory. So it's been in there for years and years and years, and it makes sense for a lot of the ARM ecosystem, but it does not make sense for x86. But no one has ever tried taking it out of common code. So if someone's already fixed that, then I will welcome the patches. If not, I have some suggestions on how to go about fixing that and make it a proper bit that the architecture, or indeed the board-specific build, can opt into or opt out of, because it makes a massive difference to the code generation.
it's quite interesting because that code was x86 in the past, and then we moved that to common code for ARM. And I'm a bit surprised it's been kind of impossible to remove it now.
So it has never been a correct thing on x86. It was put in under the expectation that there was going to be an x86 platform in the field that relied on it, and it never shipped. And that was like 15 years ago.
I would certainly be interested in your suggestions on how to solve it or help out with that, it does add a level of an extra layer of indirection in the virtual address macros to kind of trace how exactly you're ending up with the transformation between MFNs and the other various types of addresses.
Yeah, it's a mess.
But also bear in mind that if you have address space like on ARM, you do save quite a bit of space by using PDX. I vaguely remember Stefano saving, was it half a gig on the links you saved, Stefano? Not sure if it's still on the call.
He dropped
It's valuable. It is a valuable technology to have, but it should be freely able to be opted into or opted out of. And at the moment, it doesn't compile if you ever try and opt out of it. So this is a bug we need to fix.
Okay.
So, if nobody has anything else to cover, I think I'm good.
I think one recommendation is that if you have any cleanup already done on the patches and with commit messages, I would recommend to send them now without the RISC-V, so we can start cleaning up the code before you send all the bulk of patches.
Okay, duly noted. Absolutely, I can get those up.
Yeah, or even just a single email identifying the areas that have showed up.
Yeah, that sounds like a plan. Low-hanging fruit too.
In reality, we want to clean this up in Zen, but the only time it ever actually shows up and manifests a problem is when a new architecture comes. So we are desperate to use this opportunity to actually make a decent improvement in the status quo.
I don't want to make this go too much. Where are we at on time?
We got 10 minutes before the next session, so we should probably try and wrap it up sooner rather than later, but do go ahead.
Yeah, the only concern that I have with, for example, getting the build up on CI is the, well, no, that shouldn't be an issue. Yeah, never mind. Yeah, never mind. I was going to say that there are some commits that we certainly don't want upstream that enable the build, but I think if we just jump into the hypervisor directory and build from there, it shouldn't be a problem. So
yeah, I'll play around to start with.
Okay. Great. Well, thank you guys.
Thank you very much.
Thanks, everyone.
Thank you. Looking forward to see the results.